Hello, everybody. Good afternoon to everybody. Well, good afternoon from Chelsea anyway. A very warm welcome to the 2021 CGU online series of research presentations that are running through both June and July on most Tuesdays and Thursdays this summer. Our session today is Permafrost, Hydrology and Hydrogeology, Interactions, Innovations, and Challenges. We're delighted to have speakers contributing to today's session from across the country. My name is Peter Morse. I work with Natural Resources Canada, and I'm one of two conveners of today's session, along with Chris Spence from Environment Canada. I'm joining in today's session from Chelsea, Quebec, which sits on unceded Algonquin territory. We're grateful to be able to live and learn on these lands with all our relations across Canada. I offer this land acknowledgement to have us pause and reflect on our Pan-Canadian session today, a chance for us to individually acknowledge the history and Indigenous peoples of our respective regions in the ongoing work of reconciliation. Just before we start with our speakers, I want to mention that after the session, we will run a promotional video at the end of the session for next year's annual CGU meeting with the theme of Science Serving Society. This will be the first in-person meeting that's run since 2019. So it will be very exciting to attend, and we hope to see you there. During these presentations, if you have questions, we encourage the attendees to use the Q&A box to either type out a question or indicate that you would like to speak a question out loud, and then we'll allow you to talk. So without any further ado, our first speaker is Vincent Haagmans. His affiliation is with ETH Zurich, and he's going to be telling us about modeling transient permafrost at the northern tree line, the influence of snow vegetation interactions on active layer dynamics. Welcome, Vincent.
Well, thank you for the kind introduction. I am Vincent Haagmans. I'm a master's student in environmental engineering, majoring in hydrology and water resource management at ETH Zurich, Switzerland. And in the upcoming 12 minutes, I want to share some preliminary results of my master thesis and what I eventually hope to achieve until the end of October, meaning that I'm currently halfway through my thesis project. And now, first of all, what is the relevance of my project? Well, this first slide already gives a hint. So on the bottom, you can see a very smooth snow surface, which is snow depositions in a river valley in our study area, Trail Valley Creek, Northwest Territories. And then if you go into the upper left of the picture, you see a rather, let's say, rough surface. Whereas on the right side, there's a group of black dots, which are trees. And going to the upper left from these trees, we see a nice plume. And this plume is snow distribution or redistribution behind these trees because of influences on the wind field. Now, so we see a very complex interaction of topography, vegetation. So this is something which is of relevance for these permafrost areas because of the insulating capacities of these snowpacks. Now, so what is the further motivation for this study is actually something we're observing. Okay, the GIF is not working. That's a bit of a bummer. But anyway, what we're seeing is a shrubification of the Arctic tundra. So instead of grass, we have more shrubs. And this has been an ongoing discussion in the scientific community in terms of what is this going to do with our permafrost, and what are the thermal impacts of this vegetation. So either is it going, and this study by Way and LaPalme went into this, and they are arguing that the net ground surface temperature impact of this increased snow trapping, because higher vegetation will lead to more increased snow trapping. And this will by far exceed cooling caused by enhanced shading following this increase in tall vegetation in summer. So another thing which came up in our study area, a study done by Inge Grunberg from the Alfred Wegener Institute, they found a very strong relationship, or a strong relationship between vegetation type and end of winter snow depth. So again, this interaction shows up, and also the complex associations with late summer thaw depth in this permafrost area. Now in the 21st century, we're expecting extensive shrub expansion in the tundra. So the question needs to be raised, how does snow depth as a function of vegetation cover govern active layer dynamics in these permafrost areas? So in terms of temperature, thaw depth, and also soil moisture content, as well as runoff. As well, another question which we're interested in would be what might be the impact of the upright vegetation expansion on active layer dynamics at the continuous permafrost zone. In this case, at the northern fringe of the forest tundra transition in Northwest Canada. So let's take a little trip to our study area. In this case, we're looking at Trail Valley Creek, looking northward, and we're actually focusing on a subcatchment of Trail Valley Creek, being Siksik Creek, which lies at the tundra taiga transition zone. And like we already can see in these two plots, is that we're having different kinds of vegetation in this area, making this very interesting to study, because we have all these different kind of vegetation zones interacting in this permafrost region. And we're having 100 to 150 meters of continuous ice-rich permafrost in the area. So ice-rich is important here because once this thaws, it will lead to slumping, like we're already seeing around the Arctic. So understanding what's happening in these areas is crucial. As well as still currently having 25 to 100 centimeters of active layer depth. And on the right, we can see how heterogeneous the snow cover is. That would be the right plot related to these vegetations. Now, what is the approach we're using? So we're using a land surface model called CryoGrid. A CryoGrid is actually a proven permafrost model in development since the 2013s. And has been used all around the Arctic. And what it does is basically it is a 1D representation of the soil stratigraphy in a tile form, and it can have lateral fluxes with other tiles. So we more or less have a semi-distributed model. And this breaks down into having a snow domain and a soil domain. And the snow domain, which is of course on top of this soil tile, can either be a simple snow model or can be a more advanced crocus snow model. And this crocus snow model is of interest because it has a certain number of processes which are very relevant for the Arctic, like wind blown snow compaction, redistribution of snow, and so on. And in the soil domain, we basically have all the processes which we want to be modeling in, we want to include in our permafrost models. So that would be, of course, heat transfer, hydrological schemes, excess ground ice, also subsidence. So this is a bit how the model, or the 1D tile of a model looks like. Now, if we combine these two tiles, so that would be, for example, an upper tile being the ridge and a lower tile topographically lower. There can be an exchange of mass and energy, in this case snow, for example, going from the higher tile to the lower tile. And in that way, we can capture most of the relevant processes in these areas. Yeah, so how have we been going about this? So first of all, we gathered, of course, some in situ data. Philip Marsh's group did a really good job of having a long-term record of a lot of different variables in this area. That makes work easier for us as well. So I'm quite impressed by this, I have to say. Anyway, based on this data, we can define some snow vegetation scenarios. And because we need continuous forcing data, we used ERA5, which is ERA5 Land, which is a European reanalysis data, reanalysis data, as well as RDRSV2, which is a Canadian model. A reanalysis model is basically a weather model which is corrected going backward in time with observations at these points in time. So we then introduced this, first of all, simple 1D model, and then added some complexity. And then, of course, once you get some improved simulations, you can then start looking 2D. And in this case, it looks like this. So we're adding a valley tile, so we can have snowy distribution. So let's go into the preliminary results. So the first thing we bumped into is bias forcing data. Now, this could have been expected because of the grid size, which is rather coarse for our forcing data. But one of the things we observed and which is relevant for snow redistribution is too low wind speeds. So we can see this for every single month. P on the y-axis being the probability, on the x-axis we got the wind speeds, and for every month we got an underestimation of the wind speed. Now there are some really cool tools around which can correct for this. For example, the quantile mapping bias correction approach. And what it basically does is that it matches an observed distribution to a simulated distribution by applying a percentile specific bias correction. And by doing so, we were able to bias correct our wind speeds. So in this case, in the left plot, we're having wind speeds unbiased or biased in the lower, which are yellow in this plot. Orange would be the corrected data, blue are the observations. So we're seeing a significant shift in the wind speeds upwards. Now, another point we bumped into was the underestimation of snow water equivalent. This plot is a bit messy, so I calculated for you, or the MATLAB did that for you, the differences between observations, TVC observations of snow water equivalent at the end of winter, compared to a number of reanalysis forcing data sets we're using. And what we're seeing is that the Canadian model is doing a bit better, but on average, we're having 10 to 20% less snow water equivalent at the end of snow compared to what we're observing. And then we're not even including sublimation. So sublimation is the transfer of a solid snow or snow into the atmosphere, into a gaseous state again because of wind blown processes. And this would be about 20%. And if you add that into the equation, you're having 50% up to 50% less snow produced by these models than what you're actually observing. So that's problematic, but we can account for that by using a snow correction factor. Now I'll stay with the snowpack because it's very relevant for our permafrost model simulations. Because getting the snowpack right is the difference between either getting permafrost in a model or not getting permafrost in a model. Now, using a simple snow model, we're actually getting the soil thermal regime rather well. But then if we were to use a more advanced model, because the simple snow model doesn't have, for example, the redistribution or snow compaction, and in this case, we don't have a fixed snow density. And in this case, what we're seeing is that we're just not getting any permafrost because of too fluffy snow. So that was a problem. Then another point which we had to consider was getting snow at the right point in the year. So the onset of the continuous snow cover needs to be right because of the insulating properties of the snow. But what we found is actually that it fits really well. So the data we're getting from these reanalysis data sets are giving us snow at the right point in time. So that is actually something which is modeled correctly. But then we still are struggling with the too high the too low snow densities in our more advanced snow model. So if we were to not use redistribution but only snow compaction in our model, we're having in a 1D model set, we're seeing that the soil temperatures are not modeled correctly. Now, if we take redistribution into the equation for the same tile, we're seeing that the snow water equivalent definitely goes down like we hope to, and in this case, it produces much better computations of the soil thermal regime. So this is definitely something which needs to be taken into the equation when you're using these advanced snow models. I'm having a small problem here. Okay. Okay, so the current work, something which I'm currently working on is soil moisture content, getting that right. Because of the soil thermal regime being influenced by the heat capacity of water. So something needs to be right, and we're working on that hard. And then future work would be to improve these 2D simulations, test vegetation scenarios, and then force it with a number of climate scenarios up until 2100 to see how the permafrost will react. And implications of this work would be to indicate whether permafrost degradation in TVC might occur in observations and tell these researchers where to go based on some campaigns which were flown by these airplanes. And with that, I want to stop my presentation. Thank you for your attention. And if you have any questions, I will do my best to answer them, as well as feel free to reach out to me either to ResearchGate or Twitter. I'm happy to chat about what we're doing here.
All right, well, thank you very much, Vincent. If there's questions, please type them into the Q&A. I've got one just to get things going. And it's just on the theory side, you know, snow is a winter condition, freezing setting, and active layer development is thaw during the thaw season. And so what are the connections between snow depth and active layer? And I know that vegetation is interposed there, but yeah, what are the connections, and how will you be separating out sort of the influence of snow and versus the influence of vegetation?
So these snow vegetation scenarios we're trying to come up with are based on the amount of snow which is trapped by a certain type of vegetation. So in that way, we're trying to figure out how different vegetation would lead to different kind of active layer depth. But I have to acknowledge that there's so many processes going on in these environments that it's very hard to get a clear signal out of the output you're producing. So there are definitely some limitations to this modeling approach, but currently that's the best we got, and I hope that answers your question. I'm not hearing you, Peter. You're muted.
Sorry. First question, and we've got another one from Élise. First question from Chris Spence is, why are you using the gridded data when there's access to observations?
The gridded data, the reanalysis data, I'm assuming that he is referring to. So the forcing data.
Yeah, that's what I'm. Yeah.
So the thing with these observations is that they, for example, when it comes to precipitation, we have a significant undercatch, which we don't really know how much snow is falling, for example, and also the data we're having at this site has some gaps, and then we would have to turn into gap filling of our observations, which obviously also leads to some kind of bias. So there's really no nice way to working around having gaps in your data, observational data, meteorological data.
Do you have any follow-up, Chris?
Oh, that's great. Thanks.
Great, thank you. Élise has a question.
I actually had the exact same question as Chris. I guess I have a lot of observational data, and for my modeling work, I spend a whole lot of time on gap filling, so I totally understand that you don't want to do that. And so your explanation there, adequate, thank you.
And then also, I need to add on that is that while using these gridded data sets, you have some consistency in terms of running it backwards, but also into the future. I mean, the biases we're having in these reanalysis data sets also feed into the future climate scenarios, right? Where we might be using to force cryogrid. So having an idea of that in these reanalysis data sets, some biases is already quite nice. I think it's just no perfect approach to this.
There's another question, Peter, in the chat or in the Q&A. If I can go ahead, if that's okay.
Yeah, sure. Yeah,
sure. And so Vianette's asking, did you evaluate the vertical profile of snow density simulated by Crocus?
Yeah, we did. So what we're observing in 6 Creek and 12 Valley Creek is depth hoar in the snowpack, and that is something which is rather hard with the version we're using in the Crocus version we're using to model that correctly. So we're not really getting any depth hoar in that in our snowpack, but this is definitely something we're constantly looking at. getting the snow densities right. And that is one of the struggles we're having, because snow density obviously feeds into the heat conductivity of the snowpack. So that is definitely something we're looking at and trying to get as right as possible with the limitations of the model.
Great. Well, thank you again, Vincent. Super interesting talk. Can't wait to find out how this progresses. We'll see.
Thank you.
Thank you. Our next speaker is Mason Dominico. Mason is with Wilfrid Laurier University, and he'll be talking to us about spatial variations in seasonal thaw rates on a subarctic peat plateau. Welcome, Mason.
Okay, thanks for having me. So thanks for joining me. My name is Mason Dominico. I'm a research technician and MSc candidate from Wilfrid Laurier University, working with Dr. Quinton. And for this talk, I'd like to discuss some preliminary results from my master's thesis centering on the spatial variations in seasonal thaw rates on a subarctic peat plateau. This study takes place in the southern Northwest Territories, about 50 kilometers south of Fort Simpson. Situated in the lower Liard River Valley, the Scotty Creek Basin is a 152 square kilometer wetland dominated basin overlying discontinuous permafrost. This area is characterized by short cool summers and long cold winters with a mean annual air temperature of around negative 2.8 degrees Celsius. In the Scotty Creek Basin, permafrost is typically constrained to peat plateaus, which rise roughly 1 to 2 meters above the surrounding wetlands and support a canopy of black spruce. As a result of their relatively elevated surface, peat plateaus act as runoff generators and shed water to adjacent features, such as bogs, which in this landscape serve as storage features, and channel fens, which serve as broad drainage networks, slowly conveying water out of the basin. So on the left here, we have a satellite image of the Scotty Creek Basin with the study plateau kind of outlined in yellow. And then on the right, we have a classified portion of the Scotty Creek Basin that overlaps our study area, where the plateaus are shown in green. And it's important to mention that this plateau is part of a larger plateau wetland complex. Which brings us to our objective, which is to quantify the rate and pattern of permafrost thaw on this representative peat plateau. And here we can see even more that this plateau is part of that fragmented, larger plateau wetland complex and is bounded by on almost all sides by a different feature, be it a channel fen, a winter road, which was cut in 1969, a bog, and First Lake to the south. So in order to understand these rates and patterns of permafrost thaw, we investigated how this one plateau has changed since a baseline established in 2010. And to do so, we looked at the aerial extent of the plateau. We looked at the thickness of the supra permafrost layer, as well as the depth to the base of permafrost and how these have changed over the past decade. So on the left here, we have a satellite image from 2010 showing the outline of the plateau boundary in yellow. And then on the right, we have a more recent satellite image showing the contemporary boundary of that peat plateau, as well as outlined in white are some geophysical transects that we collected. And the ones in red are historic thaw depth transects that were established in 2010. And those were also surveyed with geophysical means. And so the aerial extent translates well to the spatial extent of the permafrost because the relatively steep or flat sides, such as the ones that this conceptual diagram are showing, where it lines up pretty well with the canopy. So using a combination of LiDAR-derived products and UAV imagery, we were able to delineate the plateau boundary in each respective year and then compare them. So we have the boundary taken from that 2010 image displayed as like the dashed black line, and then the boundary from the 2019 image displayed in the solid yellow, and the areas of permafrost loss highlighted in a shaded red. And after doing so, what we found was that the spatial extent the surface area of the plateau decreased by roughly 5% since 2010, with the majority of that reduction being located adjacent to the fen. So this was in areas that typically had moats, and if there weren't moats formed, they've typically expanded so that they cover pretty much the margin of the plateau bordering the fen. So after looking at the aerial extent of the plateau, we decided to use ERT, or electrical resistivity tomography, to try and characterize the subsurface. And ERT works well in permafrost environments because of the sharp contrast between frozen and unfrozen mediums in terms of resistivity. So we collected a couple of exploratory surveys in late June 2019, shown here on the right, where the black dashed line indicates where the profiles cross from the adjacent feature into the plateau, just to give a sense of boundary. And all we're really concerned about for these profiles are that the areas of high resistivity are shown here in red, or the warmer colors, and that transition from red to our yellow to red gives an idea of where that boundary is. So working our way down, the fen, what we can see here is that despite this is the location where a lot of the permafrost reduction was in terms of aerial extent, the active layer, super permafrost layer on top of that looks to be relatively stable, as opposed to, say, the road, where there is a pocket of low resistivity near the left side of the profile, and that's actually the road itself. So like I said, it was created in 1969 by artificially removing all the trees. And then we can also see kind of an area of low resistivity extending from that winter road laterally onto the plateau, and moving across that profile near meter 42 to 48. We see a pocket of low resistivity that could be indication of a talc. And the talc formation is key in terms of permafrost persistence, because that talc essentially caps the permafrost itself and redirects thermal gradient down towards the permafrost. Moving down to the bog, we can see here that, as opposed to, say, the fen transect above, there you can see almost distinct frost table topography on there with some depressions. And then moving on to the lake, we see an area of low resistivity indicating kind of thawed ground expanding underneath the plateau itself, which is something we don't necessarily see on these other transects. And then if we take a closer look at these transects by essentially cutting off the bottom half and looking at the near 6 meters to the surface, we can see that on the road, those areas of thaw are highlighted even more, as well as on the bog. So after we collected these transects in June, we went back in August to collect some more geophysical transects, given that that's when there's the greatest extent of active layer thaw. So we collected one shown in white along the fen, and then on the road again as well. The road being that this is one of our long-term comparison points to compare to our 2010 baseline. But when we look at the fen, we can see that the green portion indicates almost what is thawed above the permafrost itself, and it seems relatively near surface until you get into the interior of the plateau. Looking down towards the road, we see that there's actually a thicker super permafrost layer there, and what appears to be around meter 24, still permafrost existing at depth beneath the winter road. So after we looked at each of the adjacent features, we looked into the temporal comparison, thanks to some work done by McClymont et al. In 2010. We repeated that transect, their transect being the 2010 one indicated by the yellow dashed line, and ours being the 2019 one given by the black solid line. And this was to basically compare what their inferred depth of permafrost was. And they were saying in 2010 that permafrost extended to a depth of about 10 meters based on a certain value, which was 5,000 ohm meters. So we looked for that value again and found that those values only extended to depths of approximately 9 meters. So based off of all that, we can come up with a couple of estimates. If we look at just the aerial loss based on the reduction in surface area of the plateau, we come up with that 5% number, or 845 square meters between 2010 and 2019. And now, given what we know about the permafrost morphology, if we're assuming that that permafrost extends to depths of 10 meters and is now permafrost-free terrain, that equates to a loss of almost 7,900 cubic meters of permafrost, but still roughly around the same percentage. But because we have super permafrost layer thickness from 2010 to 2019, along with ERT profiles and the boundary extent, we can do some other estimates as well. So taking a conservative approach where we just compare the super permafrost layer thickness with the change in aerial extent, we get almost a 7% reduction in volume of that plateau itself over that decade. And if we include the results or the preliminary results from our ERT transects as well, assuming a 1 meter decrease in depth to permafrost base, it results in almost a 14% contraction of that permafrost volume since 2010. And then with the thickening of the super permafrost layer, we can see these different talc formations on top of the permafrost, which are effectively sealing the fate with the geothermal flux chewing away from it at the bottom, and these talcs capping the top of the permafrost, preventing them from losing energy over winter. And that's all I have for today. Thank you.
Yeah, why don't you go, Chris? Yeah.
Oh, I'll go. Oh, thanks, Mason. That was really good. I got a bunch of questions, but I think that people in the Q&A should go first. Masaki says very nice work. They ran the ERT surveys in 2009 and saw the boundary between the peat and the clay at 3 to 4 meters depth in the thawed areas close to lakes and the fens. But that was not obvious in the ERT images that you showed, and he's just wondering if you noticed the boundary.
Based on the profiles that I've processed, I haven't seen a distinct boundary pop up other than that between the adjacent bogs and the plateau itself.
Okay. Well, he's maybe thinking about a follow-up question. I've got one. I guess, do you feel that, or do the data show that it's the thaw is mostly from the top down, or sort of coming in from the side? And I guess what I'm wondering is, can you separate out the two when you sort of in your last slide here, when you quantify the volumes and that have been lost? Can you differentiate between how much is being lost from the top and or from the side? And is this changing?
Yeah, I'm sure there's a way to do it, but in terms of pulling it out from the ERT, I think that might require more work on my end. So in lieu of those, I've been using the long-term thaw depth transects that were established in 2010. That's kind of a proxy for the super permafrost layer thickness, just because it's so heterogeneous.
Okay, thanks. And maybe this might be the last question, but are the existing fens possibly associated with previous thaw periods?
That is a great question that I'm not sure of offhand.
That is a great question. That might have me. Oh, and Masaki here. Just a quick comment from Masaki, because the ERT transects did not have thawed areas at both ends. It's not possible to detect the bottom of permafrost in your survey. So he's wondering if it's difficult to tell the horizontal versus the bottom up thawing from the data set. So I guess that's a good point.
Yeah, and that has been tough to tell, just given the characteristics of the fan and getting the ERT out in there.
Right.
But,
oh yeah. Oh yeah, that's great. Maybe we should move on now, Peter, though.
thank you.
Thanks.
Great. Well, thank you, Mason. Yeah, again, there will be lots of interesting things to see coming out of this work. I've got a few questions that I may follow up later on. It's interesting work. Our next speaker is Mahkameh Taheri, and she is with University of Waterloo. And Mahkameh will be talking to us about developing an upscale hydrological model to quantify the hydrological response of wetland cascades in discontinuous permafrost landscapes. Welcome, Mahkameh. Mahkameh, we don't see or hear you.
Hello.
Hi,
Hello?
we hear you.
Oh, sorry.
Yes,
I
now
have
we hear you.
internet connection. Yeah, good.
And you
So
can.
I'm going to share my screen. Can you see my screen?
Yes, excellent. Thank you.
Okay. Oh, sorry. Yeah, okay. So, can you see?
Perfect. Go ahead. We seem to have lost the screen sharing. And we don't hear Mahkameh anymore. Yeah, I think that's a good suggestion. Our moderator suggested that we move on to the next talk, and Mahkameh, we'll come back to you afterward, if you don't mind. Oh, and there's a thunderstorm in Waterloo right now, apparently. Thank you, Élise. So anything could have happened. So our next speaker that we'll move on to is Kristine Haynes. And she's also with Wilfrid Laurier University. And Kristine will be talking to us. You ready, Kristine? She'll be telling us about wetland transition in thawing discontinuous permafrost, the role of hummocks, and their hydrology of treed wetlands. Welcome, Kristine.
Thanks very much. Just give me a second here to get oriented. Okay. Okay, so thanks for the introduction. I think the thunderstorm is rolling my way now. I can see from the dark clouds at the window, but yes, so just want to begin by saying that the work that I'm going to be presenting today is really a collaborative effort from all of the authors listed on this page. It's really been a group effort for what I'm going to share with you today. Oh, not going to shift on me. Let's see here if I can get this rolling. Doesn't seem to want to. Change slides for me. Oh, there we go. Okay, sorry about that. So Mason gave an introduction to this already, but really what we're looking at here is the landscape change associated with permafrost and permafrost is really catalyzing a lot of change that's happening in northwestern Canada, particularly the Northwest Territories in the discontinuous permafrost zone. What we're seeing in terms of thaw and permafrost degradation is really happening vertically. So we have peak plateaus that are forested, subsiding and entering or transitioning into wetland area, losing that forest canopy. But we also see lateral degradation, so the shrinking of these permafrost bodies from the edges. And what this is really transitioning to then is an increase in wetland area. So expansion collapsed scar wetlands here, if you can see my mouse, with these orange areas, vast areas of open wetland, very little tree cover, and really what this is resulting in is an expansion of the runoff contributing area. And so what we're seeing in terms of change then is both hydrologic and physical in the landscape. And this process has been coined wetland capture. So as these wetlands expand and there's further permafrost degradation, then we see the essential drainage of these, or partial drainage of these wetland areas. This is leading to a significant amount of reduction in terms of the water stored in these wetlands. And what we're seeing in association with that then is an increase in microtopography. So the development of little hummock microforms in these areas, and also the return of tree species. So small trees that are establishing on these hummock microforms, essentially what we're terming treed wetlands. And so that's really what the focus is going to be today. And so really what we're looking at then in terms of what this trajectory of landscape change is going to look like and what that means for hydrological processes in the future. I'm not sure why this doesn't want to change for me. Okay, here we go. So in terms of research questions then, starting pretty broad, how are these treed wetlands a permafrost feature in the landscape? Do they have permafrost underlying them, even though they have this forest canopy? Do they have permafrost? And then what are the hydrological and thermal functions of these treed wetlands? What kind of role do they play in the landscape as a whole? How are these treed wetlands essentially going to fit into the broader permafrost thaw-induced landscape change that we see within the basins? And what kind of, if we can parse out what role these really hummock microforms are playing in wetland transition and essential eventual tree establishment. And then trying to look at a broader landscape scale, what kind of prevalence are we talking when we're looking at treed wetlands in the discontinuous permafrost landscape? So all of this will be centered around the Scotty Creek Basin, which Mason gave a great introduction to in terms of its location and its mosaic landscape here. So that's really what we're looking at. So in order to establish an approach for some of these questions, then we had 4 study sites established based on the numbers here, and each of them had a plateau, a treed wetland, and a collapsed scar wetland. So we could try and look at comparing hydrological and physical characteristics of each of those 3 in 4 different settings. And just as Mason had mentioned there, electrical resistivity tomography, or ERT transects, were established in each of these sites to try and get a sense of whether or not these treed wetlands are permafrost features. Snow survey transects were established, as well as frost table, soil moisture, ground temperature, a full complement of analyses that were conducted in order to be able to get a better handle on what these systems are like. So I'm going to cover some of that today. And then in terms of hummock characteristics, and looking both at physical characteristics and ecohydrological characteristics of hummocks in this landscape. And so looking at physical measurements, height, perimeter of hummocks themselves, and then some soil moisture characteristics, both at the surface and around the flanks. And these measurements were made comparing hummocks both with trees and without trees in order to try and parse out what the reasoning is, or the driving mechanism for tree establishment on hummock microforms. And as a last kind of broader scale thing, looking at a supervised classification of these different landform types, for the first time trying to incorporate these treed wetlands to get an idea of their scale using both worldview and LiDAR imagery. So when we're looking at ERT transects then, right off the bat for some results, we can see here that we have a collapsed scar wetland transitioning to a treed wetland here, a collapsed scar again, and then a peat plateau. And so those warmer colors, as Mason has suggested, represent the presence of ice. So very clearly displayed in the permafrost plateau, but we do not see any kind of presence of permafrost in these treed wetlands. So they're low lying, similar to a collapsed scar wetland, but without any kind of underlying ice. Other than the fact that in another transect that we looked at here, we do see ice bulbs. So very small masses of ice, not nearly on the scale of a permafrost body. And these are likely to be seasonal, but we have to confirm whether or not they indeed are permafrost based on interannual evidence. That's something to be looked at into the future. In terms of ground temperature, these treed wetlands, so treed wetlands are the intermediate gray color here, collapse scars being the darkest black, and then the peat plateaus being the lightest gray for all of the next suite of images. Looking at ground temperature over an annual cycle, then treed wetlands are essentially intermediate between those of collapse scars and peat plateaus. But in terms of looking at the freezing period, so looking over the overwinter months, we see that in comparison, particularly to collapse scar wetlands, treed wetlands have a lower ground temperature and a longer period of freezing. So there's a similarity with collapse scars and treed wetlands early on in the freezing period, but more so like a peat plateau later into the winter season. So that shift in temperature regime might indicate these treed wetlands may act a bit of as a thermal buffer in the landscape. So we'll kind of turn back to that later. In terms of snow cover then, looking at snowpack, snow water equivalent on the left-hand side and snow covered area on the right-hand side of this plot. Again, same color scheme and very similar to the temperature regime. Treed wetlands have an intermediate snow water equivalent throughout the season, particularly near the end. And so again, hydrologically acting as an intermediary between these two types of land cover types. And so really there's a lot to get into with this image here, but thinking about where these treed wetlands may be located on the landscape may very much have a significant impact on how they function thermally and hydrologically, particularly if it's bordering a peat plateau, may have a protective ability against some of the advective energy from that collapse scar, versus if the collapse scar is directly adjacent to the peat plateau. That is something to be further considered, but we do see the scenario in terms of setting in both considerations here. So thinking about these little hummock microforms, so accumulation of organic matter very similar to what we would see in a southern boreal kind of system that are popping up on the landscape. And so looking at just their physical characteristics then, and maybe driving some of this change to a return of a forest cover, we see that there's increased, or the hummocks are taller if they have trees present on them. So they seem to the tree establishment seems to be more likened to the taller hummocks, particularly in the wetland environment. So trying to get away from having wet feet, those black spruce roots, particularly in the collapse scar here in the yellow, we see a distinction between those without trees and those with trees in terms of hummock height, with the taller hummocks having trees present. And so very likely either through direct support, physical support for that tree establishment, or in terms of soil moisture based on what kind of setting those trees are preferential to. There are differences in terms of the hummock soil moisture around the edges of those hummocks based on landform presence, as we would expect. Collapse scar wetlands are quite wet, plateaus relatively high and dry, and the treed bogs or treed wetlands essentially falling in between those two conditions. With the soil moisture of treed wetlands with trees present seeming to be quite distinct in terms of their overall soil moisture. And so that might provide a bit of a Goldilocks zone for the reestablishment of trees, at least a preferential establishment of trees in these landscapes. And so thinking on a broader scale in terms of how this trajectory of change picture really seems to fall into place then. It's been well established that permafrost thaw results in these open collapse scar wetlands forming. And what we are kind of contributing to this then is that with the partial drainage of these wetlands as they become connected to the main drainage network of these broad, vast landscapes, then we have this increase in sphagnum net primary production, resulting in hummock microtopography formation with the potential of supporting these ice bulbs based on the thermal differences that they provide. And those hummocks then provide support and correct soil moisture conditions for the establishment of a bit of forest cover, not nearly to the density that it was to begin with peat plateaus, but somewhere in the intermediate range. And so really what we need to look at here then is moving forward then is these presence of seasonal ice bulbs, whether that in fact indicates permafrost aggradation. As has been suggested previously, it's hard to really think that that would be the case given the rise in warming temperatures, but that's something to look at, that interannual ice and what that really means for the landscape in the future. In terms of overall coverage, we're almost getting to the end here. We have the classification of the landscape, and so what previously would have been likely characterized as peat plateau because of its forest cover is in fact treed wetland when we look at it closer, because it's low-lying, similar to collapsed scars, and it is quite significant in terms of overall coverage, with about 12% of the landscape in 2018 represented by treed wetlands. And again, very much in terms of their situation in the landscape, either centrally located within larger wetlands that are connected to the drainage basin or the drainage network, or along those margins. So that will have an impact on the thermal and hydrological processes. So just a brief wind up then, treed wetlands now we know are permafrost free, but have these seasonal ice bulbs that may have an impact on future landscape change. And there is a considerable area that is at this advanced stage of change that we see now that we are able to classify these landscape types, and really to dig into their hydrological and thermal roles in the future. Acting as that thermal buffer may help mediate some of the change that's happening. And the suitable soil moisture conditions provided by hummocks really allows for that return of tree growth in this area. So just wrap up with a few acknowledgements there, and I imagine I'm probably over time. So thank you very much. I'm not hearing anyone, should I be? Sorry.
Oh, sorry. It's
Okay.
just taking me a moment to.
It's very likely that it's me, so thanks.
No, it's, yeah, I've got a question for you, Kristine. I guess as you were giving your talk, I guess I was thinking about this in terms of like a landscape evolution, and you showed that one slide. Maybe Olivia is going to cover this later. So are these?
I can go back to it if you like.
No, that's okay.
Okay.
Are these treed wetlands, are they grading, or are they like are getting or degrading across the landscape?
That has been a consideration. Thinking that it was this was first conceived a couple of years ago, it was the thought of potentially this is a plateau that's degrading and we have a bit of a relict forest cover that was remaining. But as we see, there's a very significant change between when there's forest cover to essentially obliterated forest cover because of that collapsed scar wetland. So that increase in saturation just absolutely wipes out the forest in quite short order. And so we're seeing this in areas that has undergone pretty much sustained drainage over time, and where there may be a potential for some areas to be relicts. It really is based on the landscape observations that this seems to be an evolving, developing landscape type rather than the result of previous change that's just kind of the last stronghold in former plateau areas.
Jim Buttle's got a question. What do you think comes first? The presence of ice-cored hummock promoting the initiation of tree cover, or does the tree cover help preserve the ice bubble and promote the growth of the hummock?
That is another $64 million question in terms of how that may proceed. So I think in continuous permafrost areas where they see like an ice-cored hummock form, I think there is that expansion of the ice that's then providing the lifting mechanism for that hummock to develop. Here, that is something that we need to be looking at, but it's our working theory. We're still considering both, but our working theory is that these are differences in net primary production that are causing this organic matter accumulation more so to a southern boreal kind of hummock hollow microtopography. And then that is allowing that thermal distinction in terms of that insulating snowpack, or not snowpack, insulating peat cover is allowing that seasonal ice to form. So this is something that really needs to be examined more closely.
And Masaki's got one more question. he can follow the first 4 steps in your diagram, sort of the evolution. But the last one that goes from patches of ice to continuous permafrost, he's just wondering if you have a good hypothesis about how that might happen.
Yeah, so in terms of the latter stages of it, I don't really think there is a good mechanistic explanation for how you would go from patchy ice to continuous cover, especially on the timescales that we would be considering. But that seemed to be the working theory, particularly in the 90s, for a lot of papers that were published, was that eventually with the return of small ice patches, that it would somehow allow it to end up being a continuous ice mass. But I don't think that would be the case here, particularly with the warming air temperatures that everyone is seeing, particularly the north, very hard. And so I don't think that would be necessarily the case. It's not necessarily a never, but not likely in our immediate futures. There, hundreds of years timescales.
Okay, thanks.
Thank you.
Do we have time for one more quick question? Oh, no, we don't. Okay.
We'll follow up later, maybe.
Great. Thanks, Kristine. That's great. So because of some of the weather issues that some of our speakers are having, Élise asked us to pass her over as well for the moment. So just so everybody knows, what's going to happen is we will move on to Olivia, then Tim, and we'll return to Élise, and we will wrap up with Mahkameh. Okay, so our next speaker is Olivia Carpino. Olivia is at Wilfrid Laurier University, and she was waiting to talk to us about peat plateau wetland complexes, form, hydrological function, and permafrost thaw. Welcome, Olivia.
Awesome. Thanks so much. So as Peter said, I will be chatting today about peat plateau wetland complexes, their form, function, and today I'll specifically be focused on how they are reacting to permafrost thaw. So just to I'm going to try and keep the introduction pretty brief, but obviously it's pretty well understood that temperature is the dominant control on permafrost distribution, given that if we look at it in the absolute simplest sense, permafrost does require temperatures at or below 0 degrees Celsius in order to propagate. However, the discontinuous permafrost zone is also inherently defined by the fact that there is that variability across the landscape when it comes to permafrost presence or absence, despite having similar climatic conditions. Which means we really need to put in additional efforts into determining where permafrost is and where it isn't in these landscapes. And all of this is a little bit complicated by the fact that this region is not only undergoing rapid climate change, but also that the permafrost in the area of northwestern Canada, where this research takes place, is already relatively warm. So it's already rapidly approaching its thaw point temperature. Which means that a lot of the permafrost in this area may already be at sort of a state of disequilibrium with current climatic conditions, which means that permafrost in this area is limited to areas of high peatland coverage because peat provides a really excellent insulating layer that sort of protects the permafrost from a warming climate. And then within these peatland dominated areas, we find sort of these plateau wetland complexes, which both Kristine and Mason sort of chatted about briefly, where you can see sort of these areas almost on the landscape divided by sort of dendritic fen features. So now that we're sort of familiar with the relationship between permafrost and peatlands, there are also some additional intricacies we need to be aware of within these landscapes, and specifically that permafrost occurs preferentially beneath these forested peat plateaus, while the surrounding wetlands, both collapsed scar wetlands and channel fens, are typically permafrost-free and usually tree-free as well. So land cover has really emerged as a potential method of predicting permafrost condition And not only that, but also monitoring potential changes to that permafrost condition in these peatland environments. So specifically, we're seeing this transition from more forest-dominated landscapes that are also underlain predominantly by permafrost to those that are more wetland-dominated, which are typically permafrost-free and tree-free as well, although as Kristine just mentioned, there are some additional things we need to consider there. And then in addition to land cover being a really helpful way of monitoring these environments, it also sort of helps us explore what the hydrological functions of these landscapes are as well, because each land cover type sort of has a unique hydrological function associated with it. So peat plateaus are typically seen as runoff generators in the sense that they're elevated above the water table and surrounding wetlands. And then channel fens are sort of seen as features that convey water to the basin outlet. And as Mason mentioned, collapsed scar wetlands have always sort of been seen as storage features on the landscape, as they're bound by these sort of impermeable permafrost peat plateaus. However, with increasing permafrost thaw, we're seeing these boundaries be a little bit less impermeable. So we're seeing collapsed scar wetlands connect to one another and also connect to channel fens. And so this increasing connectivity on the landscape is actually allowing water to move through these collapsed scar wetland features, as well as connect to channel fens to expedite that drainage as well. And you can see a nice example of these collapsed scar wetlands connecting to other wetland features in the degradation that we've seen on a plateau from 2003 to 2020. So now just moving on to the research objectives here. So this study sort of seeks to evaluate how peat plateau wetland complexes evolve with thaw-induced change to their form, and in turn, hopefully improve our understanding of their hydrological function as well. So objective 1 is actually completed and was recently published, which was to establish the current extent of peatland dominated terrain within the discontinuous permafrost portion of the Taiga Plains ecozone. And then the second objective, which is work still to come, is to characterize the physical form of peat plateau wetland complexes through some spatial analyses along a north to south latitudinal transect that runs through the discontinuous permafrost zone in northwestern Canada. So very briefly, I'm just going to go over the study region, which has sort of already been mentioned here and there. But we're located in northwestern Canada and specifically looking at the Taiga Plains ecoregion, where we have the extensive discontinuous permafrost zone in the north and the sporadic discontinuous permafrost zone in the south. And this area is basically comprised of a patchwork of both mineral and organic terrain, where, as we know, permafrost is typically isolated to these organic areas or peatland areas because of the thermal offset by insulating peat. And of course, this area is undergoing very rapid climate change as well. All right, so now moving on to some results. So here we are comparing 2 publicly available data sets that sort of show peatland dominated areas in this Taiga Plains ecoregion. So the first being a saturated soils data set, and the second being a soil carbon data set. And so looking at both of these data sets, we found that these peatland dominated areas occupy about 35% of the discontinuous permafrost zone in the Taiga Plains. And expectedly, these large peatland clusters are located in lowland areas with high histol or histosol soil percentages as well. So once we had these areas sort of mapped, we completed a land cover classification within each of these areas. And while we sort of classified all the land covers that were present, we were specifically interested in the proportion of coniferous forested area within these total peatland areas, just given the relationship that we know exists in these peatland dominated areas where permafrost occurs preferentially beneath forested peat plateaus. And then for the fractional forest areas, we calculated the mean within each degree of latitude alongside the upper and lower quartiles, where again, we're sort of looking at the 25th and 75th percentiles for those. And then we uncovered that a land cover trend across latitude was present in the mapped peatland dominated terrain, where if we look sort of along that boundary of the sporadic discontinuous and extensive discontinuous permafrost zone, we see that the fractional forested area is sort of at a minimum at that spot. Which indicates that while this landscape is still a patchwork of forested area and wetland area, these sites are actually dominated by collapse scars and other wetland features, indicating that permafrost has recently been lost from these areas and is rapidly continuing to be lost. Whereas if we move to sort of the northern extent of this study region, where we're in the extensive discontinuous zone, we see a little bit of an uptick in forest here, which I guess we would expect in the sense that permafrost would be a little bit more stable here due to the cooler climatic conditions. But again, we are still seeing that sort of patchwork landscape where we do see a large proportion of the land cover being occupied by wetlands as well. And then at the very southern extent, right along that fringe of the sporadic discontinuous before it turns to isolated permafrost, we see another uptick in the fractional forested area. However, here it's unlikely that this forested area is corresponding with an uptick in permafrost area as well. Instead, we're sort of thinking it's following the similar patterns that Kristine was just speaking about, where forests are returning to some of these drying and thawed landscapes. So this sort of brings us to a conceptual diagram where if we start at the initial stage on the left, we're looking at a landscape that is essentially completely forested and essentially completely underlain by permafrost as well. However, if that landscape experiences any sort of disturbance, we would see a loss of both tree cover as well as the beginnings of thawing permafrost. And then with increased permafrost thaw, we really see these collapse scar wetlands start to take hold of the landscape and really establish themselves. And then with continued permafrost thaw, that's when we're brought to one of these landscapes, similar to what we saw right on the border of the sporadic and extensive discontinuous zones, where these landscapes are actually dominated by wetland features. However, we also know that when these landscapes get to this point where they're dominated by wetland features, we also see this expedited drainage where water is now moving through these previously thought to be storage features, and the collapse scar wetlands are actually moving water off the landscape and expediting the drainage. And now once the drainage sort of gets to a point where these wetlands are drying out and time has passed, we start to see these hummocks start to establish in these wetland features, just as Kristine was mentioning. And with ongoing and continued hummock growth, we sort of start to see continued forest establishment to the point where we get to a landscape that from above looks pretty similar to the landscape we started with, where we're back to sort of a forest dominated landscape. However, it's unlikely that this forest would be accompanied with any sort of widespread permafrost expansion here as well, other than the sort of isolated ice bulbs that Kristine mentioned. Okay, so now just on to some of the work that is still to come. Obviously, we've sort of seen this latitudinal trend in individual land covers start to emerge, but we also want to look at what's happening to these larger aggregate features, so these plateau wetland complexes. And we're looking to present sort of a similar picture of what's happening both with time as well as moving across a north to south latitudinal gradient. And one of the things that obviously we're interested in looking at is how these individual land covers, which each have specific hydrological functions, are going to change as the actual plateau wetland complexes evolve and change with latitude. So we're going to do this basically through a remote sensing analysis across a north to south transect of the same study region, where we're going to be looking at features related exclusively to the plateau wetland complex. So whether that's the complex size or area or the perimeter, as well as we're really interested in the degree of fragmentation which is observed within these complexes. So the density of wetlands, as well as the wetland area and perimeter, as well as looking at sort of how water is moving through these landscapes and interacting with the surrounding channel fens as well as the surrounding stream basins. So just to conclude, this study helps provide a more comprehensive picture of peatland distribution and therefore permafrost distribution across the discontinuous permafrost zone. And this research helps to generate an understanding of how changes to permafrost distribution and ongoing permafrost thaw may impact these environments. And our goal here is really to give northern communities and northern decision makers more effective tools to respond to the impacts of climate change, especially when they have the potential to impact water resources as well. Thank you.
Thanks, Olivia. I've got one question. I guess I'm just wondering how much of a wrench that fire might throw into the conceptual diagram.
Yes, definitely a bit of a wrench there. I mean, ultimately, it is an example of sort of a disturbance that could move us into, I guess, what would be stage 2 of the diagram. I'll just go back now. In the sense that that would be an example of a way to lose or at least harm sort of the tree cover that is protecting some of the more vulnerable permafrost areas. And it could sort of expedite the, I guess, move from stage 2 to 3, but it isn't explicitly considered in this conceptual diagram.
Got another question from Misaki. Do you see a difference in tree community composition between the far north and the far south, or is it all black spruce dominated?
Yes, so we haven't done any sort of formal work on this, but I guess anecdotally, I can sort of speak a little bit to it. Just from some of the sites that we visited, it did appear that in the far south, it was still a black spruce dominated stand, but we did seem to see an increase in sort of general diversity of these stands. So we were seeing more white spruce than we would expect at some of these more northern sites, and also stands of tamarack, which aren't seen on the same scale as we see in sort of the more northern sites.
That's good. Yep, I think we can move on now, Peter, if that's okay. Thanks, Olivia. That was great.
Lots of food for thought. These are great. I'm loving it. Our next speaker is Timothy Ensom. Tim is also at Wilfrid Laurier University. And Tim is going to present to us some work that has a new title from what I have here: Thermal Regimes of Streams in Continuous Permafrost, Western Canadian Arctic. Welcome, Tim. It's all yours.
Sorry for the technical glitch on my part there, Peter. And thanks again for the great presentations this afternoon. They've been really interesting. And sorry for the slight error in my title, but I'm going to be talking about the thermal regime, and to some extent the hydrothermal regime of stream environments in continuous permafrost now a little further north in the Western Canadian Arctic, and relate this to the movement of water in winter. I live in Yellowknife, and I'm working with Steve Coquel of the Northwest Territories Geological Survey and with Philip Marsh of Wilfrid Laurier on my PhD, as well as a few additional partners on some related projects. And I'm fortunate to collaborate with the government of the Northwest Territories, Trail Valley Research Station, and also Laurier's Yellowknife office, as well as the Aurora Research Institute on some of this work. The work is mainly situated in the Beaufort Delta region of the Northwest Territories, shown here, and the community's transportation infrastructure, land use, and just the variability in the physical landscape make the region an important focus from both a scientific and an applied standpoint. There is a latitudinal gradient, in climate and ecological conditions. And in the southeast, as we can see here, there's spruce forest with tall shrub tundra just north of treeline, and dwarf shrub tundra going further north in the Tuktoyaktuk coastlands. Continuous permafrost underlies the region, and the regional climate has been warming since the 1970s. Streams are a pervasive and dynamic component of the landscape, and understanding their present thermal condition is really important for projections of permafrost conditions and winter flow. We know that large rivers in the Western Arctic may continue to flow to some extent all winter. However, observed winter water movement in smaller streams or riparian corridors is really highlighting the importance of improving our knowledge of the thermal regime of smaller systems. This photo here shows overflow in a small stream about 30 kilometers south of Tuk with a catchment of only about 3 square kilometers in midwinter. Streams that are conducive to winter flow can represent safety and management challenges for infrastructure like highways if flow persists for long enough in winter to freeze and block culverts, such as this site at kilometer 30 on the Inuvik to Tuktoyaktuk highway. The resulting impoundment of spring freshet can lead to embankment scour or even washout in the spring. These observations and other gaps in knowledge about winter hydrothermal dynamics and streams have led to these research questions. We need to understand temperature controls and dynamics better in order to project how a warming climate and how changes in precipitation will modify the stream thermal regime. Ground thermal conditions in and around streams are also of critical importance in the design of bridges and other drainage structures in permafrost areas. And although we know something about runoff from larger regional streams during the open water period, we don't know much about the amount or the timing of winter runoff in small systems. This presentation will focus on the first two questions here. To investigate stream thermal regime, we identify two types of stream environment, including riparian vegetation corridors and stream channels. Riparian corridors exist without a well-defined channel and simply have taller vegetation than nearby, more elevated land. Channels often have larger catchments and have defined bankful elevations in their cross sections, and usually also have riparian vegetation along their margins. The examples here are both on tundra. We also have the benefit of a great legacy of research, including thermal investigations of stream environments in the Beaufort Delta region between Wrangling River in the south here and Yaya Creek up on Richards Island. The figure shows the investigation sites of these other thermal projects. And these projects were conducted mainly to describe the environment in the permafrost of the Mackenzie Delta area and to inform planning and operation of the Dempster Highway, the Inuvik to Tuk Highway, and also the Mackenzie Gas Project. Also shown in the figure here are a few more recent monitoring sites set up since 2017 or so. We'll look first at the superficial thermal regime of a small tundra stream. This is the west-facing view from the ITH at kilometer 103, about 30 kilometers south of Tuk. The channel is shown approximately by the blue line. By this date in late winter of 2019, there was about half a meter of ice in the channel and just over a meter of wind-blown snow on top of the ice, making the landscape look more or less flat. The next slide will show how small hidden streams like this can often remain unfrozen during winter. This figure shows surface temperature for the stream bed and for the riparian margin, shown respectively in blue and green, as well as the ground surface at a hilltop nearby in dark red. In the first two winters, the stream system remained at about 0 degrees and obviously was much warmer than the upland terrain. This suggests that the stream conveys water throughout the winter, despite the surrounding uplands being really cold and being underlain by thick permafrost. The third winter, or winter 2020, was especially cold, and in that winter, the stream bed froze. The figure shows that the thermal regime of the upland landscape in red is relatively predictable from one year to the next, while in contrast, small pervasive streams in tundra regions could have a much greater interannual variability in their winter thermal condition. Data are also suggesting that this surface temperature variability may differ between taiga and tundra streams. Mean stream bed and riparian surface temperatures in a taiga environment were only 0.5 degree to 1 degree colder in a low snow year than their average over the previous 2 years. In a tundra system, annual mean surface temperatures were 3.5 to 4.5 degrees colder in the low snow year than their average for the previous 2 years. Stream snow cover has been observed to be thinner at taiga or in transitional forest sites than on tundra. And this may occur because taiga forest limits the wind-driven redistribution of snow into taiga stream channels in winter, whether snow is abundant or limited. We've just considered the year-to-year stream temperature variability at a single site and contrasted thermal conditions in small tundra and taiga streams. This figure now shows the near surface mean ground temperature and temperature range versus late winter snow depth at about a dozen stream sites. Temperature data here represent fall 2018 to fall 2019, and snow depth was measured in April of 2019. Monitoring sites are also prone to different extents of winter icing, and this figure now shows temperature versus late winter channel ice thickness for the same sites over the same period. Observations suggest that ice reaches its maximum thickness early in the winter, unlike snow. There's not a strong correlation suggested between temperature and snow thickness or between temperature and ice thickness in these streams, since the insulating effects of snow on upland ground temperatures are well known, and we know how good of a heat conductor ice is. These figures suggest that there are some other more important controls on stream thermal regime. Latitude, which is correlated with annual mean air temperature, is a known control on near surface ground temperature, and Coquel and others presented a synthesis of annual mean ground temperatures in this region to show their association with latitude across the taiga tundra transition here. Hollow triangles in their work represent undisturbed annual mean ground temperature at about 1 meter depth, and most of those values are shown in the red circle here. Filled triangles represent disturbed conditions, most of which are encircled here now, and were shown to be generally warmer than the undisturbed sites. Here we've superimposed mean ground temperatures from similar shallow depths in stream environments in blue, and they tend to plot among both the disturbed and the undisturbed terrestrial sites. We don't see the same general decrease in mean temperature with increasing latitude that we do for the non-stream sites. The size of the catchment likely influences ground temperatures beneath streams, and this figure shows near surface temperature means and ranges for each channel bed or riparian location according to catchment area. The largest on the right is Campbell Creek, just south of Inuvik, and the smallest is the outlet of Big Bear Lake near Laurier's Trail Valley Creek Research Station. We can see that mean temperature tends to be below 0 degrees when catchment size is below 10 square kilometers. Minimum winter temperatures also tend to show a strong positive association with catchment size, ranging from about -30 in the smallest stream up to unfrozen in the largest streams. Instrumentation among the sites allows us to explore ground temperature means and ranges at various depths beneath the streams. Here we're looking at ground temperatures 7 to 10 meters below streams and have adjusted our vertical axis. At this depth, permafrost is suggested to be present when catchments are smaller than a few hundred square kilometers. Although the temperature measurements beneath the 3 largest streams here are a decade or more old, it's reasonable, I think, to assume that these temperatures would be at least as high if they were measured now. Bridges may also allow us to assess the importance of advected heat as a control on stream temperature. Where bridges block snow accumulation on streams, the streams can quickly freeze to their beds in the early winter, blocking stream flow. This figure shows stream bed temperature upstream and downstream of the bridge at ITH kilometer 26, but similar results have also been observed and measured at 2 additional bridge sites on the highway. While the shutoff of advected heat in the stream may partially explain the colder temperatures downstream of the bridges, more work is also needed to quantify how much of the impoundment of water upstream of bridges is elevating winter streambed temperatures above what they would be naturally. The ITH has allowed this experimental design by intersecting hundreds of catchments with varying characteristics, and other components of this project are investigating the volume of bridge icings for insight into winter runoff volume and streams, and also exploring icing dynamics at road crossings. The occurrence of talix beneath streams has important relevance to water movement and ground stability. As we know, talix are perennially unfrozen ground in permafrost environments, and current data only suggests talic presence in this region beneath streams with catchments greater than 140 square kilometers. There may very well be small talix beneath smaller channels that we just can't confirm due to the exact positioning of thermistors, however. This slide shows the thermal condition of the Haynes Creek bridge piling thermistors based on data logged by the Department of Infrastructure since summer 2017. Haynes Creek has a wide floodplain, and because of its glacial fluvial origin, has a really coarse substrate that may promote winter water movement and thus horizontal heat advection along its bed. A talic exists between 5 and 7 meters roughly beneath the channel banks, and is very likely to be present even deeper directly under the channel. Work in the late 70s and 80s by Anthony Vankevich suggested that talix could be wider than the streams above them, especially when substrates were permeable, and these data support that. As mentioned, this work is also investigating the timing and quantity of winter stream runoff through icing monitoring. Although time limitations prohibit a more detailed discussion of that part of the work here, this series of daily photos from under the kilometer 8 bridge on the ITH illustrate typical winter runoff from about a 16 square kilometer catchment at the transition between Taiga and Tundra north of Inuvik. And I'll just start the video here. So we're into September 2018, now mid-October. We're looking upstream, and now mid-November. The bridge span is about 4.5 meters above the creek bed. We're now mid-February 2019 and mid-April 2019. And in some years, this icing grows even higher. There was even one year, early 2017, when it reached the bridge. So this obviously represents an important management challenge for infrastructure. To summarize, streams in continuous permafrost can have a distinct thermal regime from proximal upland terrain, and understanding this regime is important for understanding winter runoff. Heat advection is likely one of the most important overall controls, with local snow distribution becoming increasingly important at shallower depths in small catchments. Thermal regime is important for understanding natural environments, but also applicable to understanding the interactions of bridge structures and streams in permafrost terrain. At its current stage, this work, I hope, can form the basis of empirical models of stream thermal regime and also aid in physical modeling that can provide useful in the design, management, and mitigation of challenges related to infrastructure design in permafrost regions. Thanks again for your attention, and I'd like to acknowledge the organizations and individuals that have supported our work. Thank you.
Thanks, Tim. That was super interesting. If I can just ask a question before for some perhaps roll into the Q&A. I get where you're coming from in terms of the like larger watersheds, maybe provide more advected energy. I wasn't sure. You showed a slide that had sort of catchment area and temperature, and you had them separated out by riparian area and stream bed as well. And it seemed like the stream bed tended to be warmer than the riparian area, but those also tended to be maybe the larger catchments. So I'm just wondering how you can separate all that out.
Thanks, Chris. And that's a good observation. I think that the riparian terrain tends to be colder than the stream bed sub environments in these stream systems. In many cases, when we're looking at such small catchments in that region, it's sometimes hard to identify a defined stream channel. And when we get to catchments of only a few square kilometers, so in those cases, the site is kind of labeled riparian. And in the bigger systems, when we can actually identify a channel and install a string of thermistors more or less underneath it, we call it a stream. But that's, from an analytical standpoint, that's an approach that I need to think about more and think more seriously about whether simply riparian versus channel setting is as important to control on thermal regime as catchment area. I hope that helped to address your question.
Yep, for sure. I'll give it to Peter now.
Great. Thanks, Tim. Just a quick thank you to everybody for your flexibility in how we've had to rejig the scheduling of these talks. So next we will hear from Élise Devoie, and she is from McGill University, and she is going to talk to us about measured soil freezing characteristic curves. Thank you. Take it away.
All right, awesome. Thank you so much. And apologies that there's like a thunderstorm here and my internet was terrible. And I think that's probably what's happening with Mahkameh as well. It just started to pour again, so it stays stable enough for the duration of this presentation. So here I am talking about measured soil freezing characteristic curves. This feels really strange, having heard all about Scotty Creek, where I used to do so much research, but I'm really excited about these new results. So now I'm working with Professors Stefan Gruber and Jeff McKenzie at Carleton and McGill, respectively. And what I'm going to present today is essentially a conglomeration of data that I've kind of pulled out of the literature about measured soil freezing characteristic curves, because essentially this is what happens when I can't go to the field. So that's where we're started from today. I'm just going to give you a little bit clearly know that permafrost is warming, right? Cold warming is at more than 2 times the global average. And these changes are important to seasonal freeze-thaw regimes, permafrost temperatures, and this is actually leading widespread of near permafrost, as we saw in all of those presentations relating to Scotty Creek. Here I've just shown a figure from Biscaman et al. In 2019, where we see that essentially globally this permafrost is warming up, and this is pushing it towards the freezing point temperature. So why do we actually care? Well, I probably don't have to sell you on this one, but soil freeze-thaw processes play a fundamental role in so many features of this landscape. So they affect hydrology, geophysics, ecology, thermodynamics, and soil chemistry. Here I've just put up a hydrograph because, of course, we all love hydrographs, at least I know I do. And what I'm showing here is that in the Jean Marie River Basin, which to the Scotty Creek Basin, which we just heard a whole about, it's discontinuous permafrost, between historic period of 1972 to 1986 to a more current period between 2004 to 2018, we see a significant increase in runoff without any significant increase in precipitation. So this is one of the implications of that loss of permafrost on the hydrology. Of course, there are other implications, other factors that could be affecting this runoff, but it's thought that this is kind of the dominant thing that's changing in the landscape. So in order to be able to represent all of these changes and sort of predict them, we need some models. And if we want these models, we need a way to understand the change from liquid water to ice based on temperature. So how do we represent this? Well, that's where the soil freezing characteristic curve comes in. Here we relate the soil temperature to the soil ice content. So it's essentially a mathematical construct that relates here on our y-axis to the temperature on our x-axis here. I want to note that it's really important that here we have our freezing point, and as we go to the right, we're actually getting colder. This is kind of counterintuitive, right? So this is very, very cold. Over here, we have our freezing point. We have thawed temperatures. So let's just dive into the anatomy of this graph just a little bit. First, I want to point out our initial water content shown here, which is essentially before we start any freezing processes, how much water does this soil contain? Then we have our bulk melting point. So this we can see actually is a little bit below 0 degrees C because of a freezing point depression. And essentially this is the temperature at which phase change begins to happen. As we cool the soil further, we get to our residual water content. This is at a pretty cold temperature, usually between like -10, -20. When we get colder than that, we don't actually see a particularly large change in the water content with temperature. And essentially, this is when all of the water that's still liquid is kind of latched onto the soil particles, and it's really, really difficult to make it undergo phase change. Now, the interesting thing and the important thing right now is that as we see climate warming, we see the warming of subsurface ground ice. And so we're moving from this cold temperature to these warmer temperatures on the graph. And of course, we note that we're moving from a place where the gradient in this graph is really flat to one where it's very steep. So the way that we've chosen to implement this soil freezing characteristic curve is becoming more and more important. Okay, so let's talk about what's out there for actually representing these features. Here, the soil freezing characteristic curves in models exist to sort of relate these properties. And of course, we need them in models of permafrost thaw, inactive layer evolution, and seasonal freeze thaw. So essentially, all models that represent Canadian soils should have a soil freezing characteristic curve. And often they're kind of simplified. So we have to see things like this plot on the left here, where we either have a linear or exponential freezing function, which doesn't have all that many parameters to tweak, and it simplifies this process for the numerics involved. This often does a really good job of representing the data that we need to represent. But we can also have a more complicated model, such as the ones shown on the right here, which are more physically based. Here we have differential equations that relate the solute content, the pore shape and size, the freezing thaw temperature, etc., to better describe the physics of these processes. Now, why would we bother with such complexity? Well, the thing is that if we look into some
Élise,
actual measured soil freezing characteristic curves.
Sorry,
Yeah.
I'm very, very sorry to interrupt. Would you mind turning off your video? I think we'll be able to hear you a bit better because you're cut out now and again.
I can totally do that.
Thank you. I'm sorry.
Thank you. I'm happy to do that. And sorry about that. No worries. Thanks for letting me know. I will do my best.
All right.
My computer just told me my internet connection's unstable, so hopefully things go. Feel free to stop me again if I don't make any sense.
Okay, thank you. Carry on, carry on.
All right. So there's a really high diversity in measured soil freezing characteristic curves as they're seen in the field. So here I've just shown a plot of 5 different soils, and here we're looking at the diversity based on soil texture, but this can also depend on the soil pore water pressure, dissolved solutes, hysteresis in freezing point depression, the degree of saturation, etc. And so these more complicated physical models are sometimes needed in order to actually represent these soils accurately. Also, all of these properties can be very site-specific, time varying. So when we are actually trying to use a model, how are we supposed to actually make our soil freezing characteristic curve, or at least choose the correct one from the literature? So this leads us to a discussion of the sources of error and over-parameterization, or just parameterization, when we're actually pulling these curves. And essentially what we have is 2 decisions. We can either decide to land on an empirically based soil freezing characteristic curve, which relies on data collection at the site in question for the soil in question. Of course, this is definitely data limited. And then the other alternative is a more theoretical approach, where we need really detailed soil parameters. So in order to parameterize these more theoretically based soil freezing characteristic curves, we need our soil composition, our porosity, grain size analysis, specific surface area, and so on. Now, these values are also really, really difficult to get for each site, not to mention the fact that there's heterogeneity in these soils. And in most Canadian watersheds, this detailed data is really not available. But still, we do need to parameterize these curves, and we still need some representation of them. So how can we improve the approximations that we're making using these soil freezing characteristic curves? Well, the answer that I've come up with is that we need more data. We need data that
shows this relationship for a diversity of soils so that we can provide parameters that stand on more solid ground and improve our approximation of these curves, and also sort of talk to the uncertainty in these different measurements. And so what I've done is I've gone through the literature and tried to find all the measured soil freezing characteristic curve data that I possibly could. So essentially, I've done a literature review for the past 2 months. And here I've read 248 publications and counting. I found that 92 of these have unique measured sets. And from these 92 data sets, I digitized 365 unique data series for these soil freezing characteristic curves. And not so far. There's still a little bit more data that I have already that I need to process. And really what I want to point out is that this is like a lot. For somebody who does field work, my mind is blown by the quantity of data I have. You can see this plot that looks kind of like spaghetti. That like I just don't even know how to represent it in a way that we can understand it. So I'm really, really excited about the volume of data that we have. And so I'm going to try to break it into some categories for you to delve through some of the metadata and point to some of the interesting features that these data sets allow us to discuss. So first off, I have the process of freezing and thawing hysteresis. So I have this pie chart that shows the proportions in the literature of papers that sort of looked at the freezing limb of the soil freezing characteristic curve, the thawing limb, and both. And unfortunately, the slice of the pie that looks at both is quite small. But we do see that when we're looking at this freezing curve, we have more unfrozen water content for the same temperature than when we're going on the thawing lib. The trouble is that this freezing curve is also more stable, whereas a lot of the early work on determining these soil freezing characteristic curves looked at that freezing curve, and so that data has a lot more uncertainty associated with it. We also have a whole slew of different measurement techniques to report this data. Of course, there's different uncertainty associated with different techniques. Originally, we started off looking at calorimetry to try to determine these values, and more recently, we've moved on to more high-tech methods such as NMR and capacitance, etc. But what we can say is that most of these studies are completed in the lab, with a few of them in the field. Why is this important? Well, the concept of sample preparation is something that I wanted to look into in this data. And we see that most of these studies have repacked soils. So a lot of the studies that are done in the lab, you go out, you collect a field sample, you bring it back to the lab, you dry it, you grind it, you repack it to a known density, and then start conducting your tests on it. And essentially, this actually changes the soil structure enough to have a modification in the soil freezing characteristic curve. So if we can compare these repacked and undisturbed soils, we're not actually capturing the exact behavior of the field conditions when we do this. And this is really important to note given the fraction of papers, which is definitely most of them, in which the soil is actually remixed before these tests are completed. We can also break up these soils according to soil texture. Here we can see that we have a fairly even split between sand, silt, clay, and organic soils. And of course, this is really important because the responses from these soil freezing characteristics are dependent on that soil type. Also look at the initial water content. And so most of these studies talk about the saturated soil. So they start off with a completely water-filled pore space and then they just freeze it. Whereas some studies look at an unsaturated soil. What we see in the literature is that the difference in the responses from these is greatest near the freezing point, but as we get colder in temperature, these curves tend to converge. So this is just a brief preview of what I've collected so far. But the really exciting thing that I want to present to you is that I'm hoping to aggregate all of this data, put it into a neat little archive, and have this open access so that when you're looking for a soil freezing characteristic curve and you don't have data, you can kind of go in there and pull a soil that you think is most similar to yours, and we can make some determinations about the uncertainty in these types of measurements. I have a big ask for you, which is, do you have data to contribute? I've pulled as much as I can from the find out there, but if you have any data or soils in your specific field set, I'd be really, really interested in seeing these. So please shoot me an email if you have any data to share with me. That's all I have to present today. I'm really sorry about the internet issues. There's a thunderstorm. I really appreciate you hanging in there with my garbled speech. I also want to thank my field I mean data digitizing assistants, Fred and George, who are cats, and of course the people who responded to my emails asking them to contribute data to this. So I'm going to go back to this so you have my contact information, but I'd be more than happy to answer any questions if you have them.
Thanks, Elise. Yeah, that was great. I might have some data for you. I actually don't have any questions, burning questions, but see any in the chat.
I'm excited to receive your data anyways.
Yeah, very good. Yeah, maybe we can just go to the.
Well, I've got a question. It's amazing that you've put together this this data set. I'm looking forward to seeing it continue to grow. It'll be a great tool. A lot of the samples, because it was just a quick presentation of the sources, but they seem to be, sands, tephra, silt, whatever. Did you manage to dig up much data on, just tills where it's a mix of sand, silt, clay size fraction particles, some ground, much data on the kind of materials that you might find where there's a lot of mixed up stuff,
Yeah, totally. That's a really good question.
Not just lacustrine silts or whatever.
The chart that I presented there, yeah, exactly. The pie chart that I presented there was trying to sort of aggregate the data into some form of category. So a lot of the soils were in fact mixed, but I just kind of pulled the largest grain fraction to put them into a category. I was struggling because very few of the publications actually reported the sand, silt, clay fractions of their soil. They just kind of said, this is loam found in this site, and that's all the data that I have. And so it's really hard to include all of the metadata that would actually be really helpful in this kind of thing. But for the soils where I have sand, silt, clay fractions, that is also included in the metadata column there.
Thanks, Elise. I got a quick question from Misaki. As you know, the Clausius-Clapeyron equation gives temperature potential relation, and there are lots of data on potential versus water content. Are you planning on using those data sets?
That's a great question. And a lot of the publications that I've actually looked at so far are doing kind of you have that freezing and relating it to drying in order to actually pull out the soil drying characteristic as opposed to the freezing characteristic. And so that Clausius-Clapeyron relation it's a tricky assumption, and it works well in a lot of cases, but not so well in other cases. And so I'd actually really be happy to talk to you about this later, Misaki, because I'm sure that you have some great ideas regarding it. But there's some, yeah, it's tricky, but it's definitely something that I'm looking into.
Great. Well, thank you very much, Elise. Super interesting to hear about your work. So we return to Mahkameh Taheri. Mahkameh is working at University of Waterloo, and she will present to us on developing an upscaled hydrological model to quantify the hydrological response of wetland cascades in discontinuous permafrost landscapes. Welcome again.
Thank you for giving me another chance to present today. So I hope this time I can present it without any problem. You can see my, oh, I don't know what happened.
Yes,
so
we see your screen sharing. Yeah.
So if not a problem, I'm going in this situation. So today my name is Mahkameh, and I'm a PhD student at the University of Waterloo under supervision of Dr. James Craig. And today I'm going to talk about developing an upscale hydrological model to quantify the hydrologic response of wetland cascades in discontinuous permafrost landscapes. I don't know why it's not moving. So let me stop sharing again. Sorry, it seems that.
And Mahkameh, do you want to try full screen?
Yeah, but I cannot click on that. I don't know why. You see my screen now? It's not.
Yes, it's almost as if you are right-clicking on things rather than left-clicking.
Yeah. So unfortunate. So let me stop sharing.
What about
that.
just your arrow buttons? Do those?
Oh. Oh, good. Sorry.
Okay, great,
Yeah.
super.
Yeah. So I'm going to give a quick introduction about wetlands effects on hydrologic response of the basin. As you can see in the figure here, this shows a place in the Northwest Territories, which is full of wetlands. And we know that the hydrologic response of these places to precipitation or snowmelt event is highly affected by the presence of these wetlands, because wetlands can serve different functions based on the water available to them. They can store water and act as an storage features, but if we provide enough water for them to pass the threshold, they can contribute and overflow and transmit water to the outlet of the basin. Also, as you saw in the other presentation, permafrost thaw can change the extent of the wetlands, the area of the wetlands, and also can change forest to wetlands, transforms forest to wetlands. So they play an important role in the hydrology of a wetland-dominated landscape. So the main question of our project is to examine the response of the landscape with thousands of wetlands to precipitation or snowmelt event. And fill and spill processes is the name of the process that can define this isolated connectivity continuum or the functions, different functions that wetlands can play. For example, as you can see in the figure here, each wetland has a storage capacity, and when the available water or the precipitation or snowmelt is enough to fill that wetland to a certain threshold, they will be filled and spilled to the other wetlands in the basin or the other water bodies in the basin. And in this project, we are looking to upscale these hydrologic processes, upscale these fill and spill processes which happen at each wetland. So by upscaling, I mean that to use the information that we have at point of scale, to use the information that we have at some of the wetlands, and upscale that to find the aggregated results, aggregated outflow from our basin. And why we need that? Because we cannot look at all wetlands and see fill and spill processes in all wetlands in a basin which has thousands of wetlands. So we do upscaling here. And based on there are until today, there are lots of models which simulate wetlands effects on the basin, but there are some problems in those models. For example, some of them doesn't consider the interconnectivity between different wetlands. They just consider each wetland individually drains to the outlet, but they might be connectivity between those. They might be fill and spill to each other and then to the outlet. And some of the models consider explicitly consider each wetland in the basin. So these models needs a high resolution data, which is not available at all places, and also it makes them to be very computationally expensive. And some of the models needs lots of parameters, and it causes huge uncertainty. So these factors motivated us to propose our model, which is a probabilistic model and doesn't need lots of parameters, and it also considers the connectivity between different wetlands. So here I'm going to give a quick overview of the methodology of our work. As you can see here in this figure, we consider wetlands are in the cascading network. For example, here you can see 3 cascades. These cascades here contains 3 wetlands. Each wetland will drain to the next one and to the next one and then to the outlet. And first of all, we want to start with the wetland, which is individually drained to the outlet. And that will be a generalization of the PDM model. As you can see here in this figure, our wetland has a deficit, which shows that by D, and that will gain water from precipitation over its own land area and over its contributing area. So we need to concentrate the water which comes to the contributing area to the wetlands area. And we call that factor, we define a factor here, which is a concentrative factor, which contains the effects of contributing area and precipitation over the wetlands. Then this available water will fill the storage deficit which exists in the wetlands. And then the difference between that available water and the deficit will be the final outflow from that wetland. So we want to find what is that final outflow from thousands of the wetlands in the basin. Using the drive distribution approach, which is one of the upscaling methods, if we have the distribution function of the concentrating factor and the deficit of the wetlands, we can find the distribution function of the outflow. And that will be the integration of the products of those distributions. So how we can find the distribution function of concentrating factor and deficit? We can use GIS and find, for example, for a real basin, we can find those. Or here we just assume that an exponential distribution can represent the variability of deficit and concentrating factor over our basin. And if we substitute those exponential distribution in our integration, we can find the analytical solution. And I'm going to show you how this mathematics here will be shown. Okay, so in this figure, you can see that we have a deficit distribution in black here. This is our initial deficit. It shows that what is the probability of each initial deficit in our wetland dominated area. After precipitation, the red plot here shows the probability of outflow. And you can see that it has a positive part and negative part. The negative part shows the new deficit distribution. After precipitation, our deficit distribution will be changed, yeah? So here shows the new distribution. And the positive side shows the actual outflow distribution. And we can use that part to find the average of the outflow from the basin. And the negative side can help us to find the probability of zero outflow, and that can be used to find the probability of wetlands which are shedding water or not. So to account for the connectivity between wetlands, as I said, we consider them in a cascading network. Here, if you consider, for example, the second wetland in the cascading network, it receives water from precipitation over its land, over its contributing area, and also it receives water from upstream wetlands. And our new water balance equation will be like here. We have the terms that we had for the single wetland, and also we have the input from upstream wetlands. And we also here assume that each wetlands all of the wetlands in the basin have the same area. So it means that when we want to normalize the value by the area to find the depth, that will be simplified to 1. So again, we have 3 terms in the water balance equation, but we found the distribution function of the first 2 terms, or the outflow from one wetlands in the previous steps, and also we found the actual outflow distribution in previous step as well. So again, we can use the drive distribution approach and simply find the distribution function of the outflow and the average outflow. We also did a validation against Monte Carlo methods. What we do here is that we sampled thousands of wetland properties, I mean deficit and concentrating factor, from our exponential distribution, and then simply substituted them into our water balance equation for one wetlands or n numbers of wetlands in each cascade. And we found the results here in the right figure, as you can see here. It shows that the points shows our Monte Carlo result, and the solid line shows our analytical solution. And you can see they are perfectly matched. And different colors here represent different cascade depths. I mean, if we have individual wetlands draining to the outlet, or we have 2 wetlands in each cascade, 3 wetlands, or 4 wetlands. as you can see here, as the number of wetlands increases, our normalized outflow will decreases, which means that we have more wetlands to fill them before seeing outflow. So some of the precipitation fill those wetlands first. And then you can see that, for example, for 3 and 4 wetlands in each cascade, we see the results are so close together. It suggests that these normalized outflow by increasing the number of wetlands are reaching an asymptotic limit, which means that we can say after 4 wetlands in the cascade, the results might be the same because, for example, there must be a gatekeeper on the other part of the cascade depth and the connection will be disconnected. The wetlands will be disconnected from the outlet. So, and also our analytical solution after 4 number of wetlands becomes mathematically intractable, and it's not very easy to find, for example, the results of 5 wetlands in a cascade. But using the Monte Carlo approach, we can find the results of the response of, for example, 15 wetlands in the cascade, and it's so close to 4 wetlands, so we'll leave it on 4 wetlands. Here, I'm also showing how our model is sensitive to the number of wetlands in each cascade and the weather condition. As you can see here in this figure, we show normalized outflow based on the precipitation, and we show that for wet, average, and dry condition. So the climate condition has its effects on our deficit distribution. For example, for wet condition, our deficit distribution, the minimum deficit distribution is 0, which means that all of the wetlands are full. But for the average, some of the wetlands are full and some of them are not. So as you can see here, for wet condition, when we have a little bit of precipitation, the watershed, we have outflow, but for the dry and average, some of the precipitation first need to fill those storage, and then we see the outflow. So so here I'm going to talk about the future steps that I'm working on. We are going to implement our analytical solution in the semi-distributed hydrologic model Raven to see how is the actual response of actual basin. We want to model an actual basin and see how is the results and compare that with the existing models. I also want to thank all of you for your attention and all the contributors to this project, and specifically Dr. James Craig, Mark Randrom, and Dr. Bill Quinton. Thank you.
Thanks, Mark. I have one question.
Sure.
Before we see it, and I think it was your second last slide. You had the wet to dry conditions,
Yeah.
and the wet condition had a much more non-linear response than the dry. And I'm wondering if you have any insight as to why that might be.
So for the wet condition, it means that the deficit, all of the deficits are full because of that. So when we have a precipitation, all the wetlands are shedding water. But for the dry condition, it happens later after precipitation fills all the storage in the basin, and then we can see the outflow. So that might be because of the situation of the initial deficit.
Right. Thanks. I don't see any other questions. Maybe if it's okay with Peter, we can just move to the wrap up.
Yeah.
Yeah. Okay. Thanks to everybody. I thought that was a really good session. Sort of juggled some things, but that was okay. So credit to everybody there. I'm supposed to inform everybody that our next CGU session is July 6th, which is being run by the Biogeosciences section. The next Hydrology session is on July 8th, and that's coincides with the annual general meeting of the section. So I encourage everybody to attend to that. And I think this was going to play a promotional video for us next about the 2022 meeting. So, thanks. Just one more time, just thanks everybody for attending, and stay cool, everybody.
Yeah.
Do okay. All right. Thanks. And
Cheers. Thanks, everybody.
Bye.
Bye.